No problem. I was just saying, some places it's customary to wait 7 minutes for people to make it from one important meeting to the next. Okay, you ready to roll them?
Go ahead.
All right. I'm Henry Strickland. Half my friends call me Henry, half my friends call me Strick. Maybe I should be Strick at this conference because there's another notorious Henry attending. My GitHub is strickyak, and my domain is yak.net with the email Strick in front of it if you want to try to get in touch with me. But on the Discord, the CoCo Discord, Strick9 is my handle, spelt with the digit 9. And today I'm going to talk about NekotOS. And we've got Nekot. Today's flavor are lemon cream, cookies. I'm going to run out. We've got more at my desk. Boise. Okay.
Oh, what? None for the sound guy? Here, I'll take this one.
Okay. So, at CoCoFEST a year ago, I had this Space War game written kind of as a one-off game, and people who had Patrick Ulan's CoCo.io board like this for Ethernet were able to use it and plug in and play a real-time shooting space game. Well, it kind of moves slow compared to shooting games today. And if you ever see it running on the PDP-1 at the Computer History Museum, they're really slow, but they're beautiful. And over the year, I decided I wanted to write an operating system for building games like this to encourage other people to do it. And so I factored out of this game some stuff that I call the operating system kernel and some stuff that I call library code. And then it leaves the game in a much simpler form with a lot of things taken out of it. So it can be shared by other software. Sorry, I'm having a problem. And the operating system I'm calling NekotOS. And I put these adjectives in front of it. Real-time. It's kind of like a real-time kernel in which you can get a response to events on an order of about 1/60th of a second. That may not be the real-timest real-time, but it's real-timer than lots of computers where you sit and stare at them for a long time waiting for them to do something. Multi-CoCo, let's call it multi-CoCo instead of multi-user, because I want to stress that it's not 4 people sitting around one keyboard, but rather 4 people have 4 different CoCos. Would like to expand it in the future to work for Dragon, to work for the Phoenix 256, to work for my TFR single board computer, and if you've got another platform. Oh, and OS 9 is is kind of a virtual computer of its own that it would be nice if this could run under. And gaming, I'm going to use the word game a lot, and I've redefined game to mean whatever app this operating system runs. But we're going to call it games. And let's see how I'm doing as far as the overview goes. The overview I was supposed to, and networked. Networked is the big important thing. And relatively fast, relatively means relative to the 8-bit world of the 1980s. When you see the latency in the game and the things here, you'll kind of understand that I don't want it to slow down because you're bit banging on the modem port. I want it to be able to be a smooth transfer of bytes, and then the game can continue and you're not slowed down by the networking. But anything that's relatively fast, I'm ready to consider writing support for. So people ask, like, how fast is fast? And I'm thinking about a dozen 64-byte packets per second. Now, in the modern world, that does not sound like a whole lot. Where did I put that? Oh, there we go, yeah. Maybe a dozen. And so what that would be is if you say you have 8 different CoCos, and each one broadcasts to all the others once a second, a 64-byte packet. Plus there is a couple of other things that the operating system itself is doing. Oh, I haven't talked about the server. There is a server that they all connect to over this network by TCP. It's called the MCP, the Master Control Program. The name comes from Tron. It has nothing to do with the MCP you read about in Hacker News, which is an artificial intelligence API. Okay, real time. The operating system is working with background tasks for doing a lot of the stuff that are running inside that 60 hertz interrupt. So that's going to be important. Multi-CoCo and gaming. Now I'm going to do the demo so that before I talk anymore, you'll have a better idea really what I'm talking about. And if you can't see this screen, you might want to move a little bit closer. Here's a CoCo 2. It's only got 16K of RAM. This is kind of my minimal machine, a CoCo 1 or a CoCo 2 with 16K of RAM and the normal SAM and VDG, the normal video modes, P mode 1 to P mode 4. That's my target architecture for the version so far. And the idea is by limiting myself to this, to 1 megahertz, and to, everything I've done is P mode 1, 128 by 96 with only 4 colors. It's easy later on to start to use a CoCo 3 with double speed and better graphics and all that kind of stuff. But to prove what I can do across almost any CoCo, anything except for a 4K CoCo 1 is how I've started out. And there's a CoCo 3 down here. Now this one has Rick's CoCo IO card, and this one has my Bonobo card. And so 2 different network cards on these things, but they're both connected to a server that I have running locally on that laptop on the floor. The MCP is inside of there. But there's also an MPC. How's my audio? There's an MCP that's running in DigitalOcean, located in New York City, is where the data center is. So it's out in the cloud. And that's going to be kind of the default one that anyone anywhere in the world who wants to jump on and play games and find somebody to do it with would connect to if you're not at a conference like this. So let's watch that one reboot. The Bonobo card first loads an operating system called LoadOS, and LoadOS is used to load NekotOS. And it says my handle is YAK, Y-A-K. The handles are 3 letters like old video game handles. My name is Strick. My location is Chicago. So if I go into a clock, it's going to be in the current time. This one over here you can see is an hour ahead. It's in New York time. And let's give it a reboot and watch it boot up. So first it's going through the boot ROM that's in the Ethernet card. And it's looking for, and it did not find the server down here. It should have discovered it. Now, okay, this time it discovered it. That's a UDP broadcast protocol that I don't know why it fails sometimes. And now we're connected. Its handle is UNK for unknown. And if I hit escape up here, then this game, this is called a game, even though it looks like a clock. This game keeps running and has a console like that. And I can say who all is connected, /W, and it says unknown and YAK. And YAK is actually already in room 77. That's this machine. So I'm going to take this other one that just joined, the unknown player, and join room 77. And then I can say who all's connected now. And it shows unknown is in 77 and Yak is in 77, and unknown is player number 2. So this is a little bit of a bug. It should have been player 1, but there's an orphaned record in there from the previous time we ran. That's all right. Player 0 is the king of the room and gets to decide what everybody's going to play. And let's play Space War, says the king here. So they both jump into Space War, and Space War lets you spin around and shoot bullets at your opponents and fire a bullet. And I'm hoping that bullet is going to hit these people right here eventually and score a point. But I might have to move forward and chase after them a little bit. Anyway, once one scores, the points move to the other one, and both of those screens should be within like half a second or so of showing each other the same game state. And that's what my talk is really about, is how do you write a game so that everybody sees the same thing, sees the same scores. This is kind of pathetic that we don't have any score yet, but it's hard. Turn around and go point that way. Fire a bullet. Okay, I'm going to kind of leave it at that. At any point, either player can hit break and they get back to here where you can chat and say hi. And if that guy also goes break, it shows up and he can say hello back. And so you're always in a chat world, but you've also got these commands. It's kind of like IRC. You've got commands that let you do things. And here's another game. This is the cow glider. And one of those pucks is me. I'm starting to move. And if I cross any of these cows, I get a point and the cow goes away. And this one can start gliding around as well. And so you see it's on both screens gliding the same kind of way. And if there's no bugs in there, okay, 2 points and 3 points, 2 points and 3 points. So it's working. So the rest of the talk, I think, will make a little more sense once you've kind of seen what the goal is to be able to write games like that. And I'm looking for more people to help with this, of course. Back to the slide presentation. Okay, at this point, AV, we're done with the screens here, and we can show the slides over here. We talked about networked, we talked about real-time, talked about multi-CoCo, how there's a common server named the MCP. There's a chat that's available to you. You can team up in a room so that you can launch a multiplayer game with those folks that were in that room in the same game shard. You can use the chat to get help, do collaborative debugging. I assume that you'll still have Discord or something going on the side. Won't try to replace all of that for the communication. Game is any app or any program that this operating system could run. Those could also be clocks, could be picture galleries, movie players. Like last year, I was demoing some YouTube videos that I had converted and made stream onto a CoCo 3. Information kiosks, like in the middle of the room out there, there's a 16 by 16 pixel kiosk that kind of shows little animations and things. I'd love to have that on these CoCo screens next year to get some artists together and gather your favorite CoCo art. I'll scrape some off of the Discord as well. So Nekot is an operating system. It's minimalist. It leaves out anything it can leave out. It's microkernel-ish in the sense that things microkernels deal with is setting up processes, setting up a flow of control, mapping some memory, and starting a task, and communicating between the tasks is kind of what microkernels provide, and that's really what Nekot does. The exception is Nekot also gets into networking and has a network driver. Like there's a driver for each of those two hardwares I was using earlier. The network is really the heaviest component in Nekot. The whole kernel fits in 4K, and as much functionality as possible is pushed into the MCP server. And that's not gaming functionality, that's all the side associated things. The chat, the downloading of software or the downloading of other content. Rendezvous, where you get people together in a room, that's all done in the MCP. Collecting top scores when the game is over. The kernel really depends strongly on a 60 hertz interrupt service, because like when the game is going, that's the only way the kernel continues to keep control of things is during the interrupts. And ordinary things that you find in operating systems, like a standard in path, a standard out path, disk, the joysticks, pretty much the video screen. It's all, if you're going to use those or need something like that, you write it and you put it in your game, or you get it from the libraries that the games can link with. A little point about retro purity. I always have to mention this because once I have a server in the internet that's running on a Linux box, some people are going to diss it, and that's fine. Everybody gets to choose what their ground rules are for retro purity. But what I want to see is that the gameplay and the dynamics of how the game works runs fully on the CoCo's. It's okay for the server to act as part of the internet, just forwarding packets to other people inside your game shard, and the server provides these other functionalities. Chat lets you issue other kinds of commands, rendezvous with other players, download the software, collect top scores, provide the time of day to the games, and I'm finding that I want to get random seeds out of the server. That games need that. And I mentioned my initial hardware is any CoCo with at least 16K of RAM and VDG graphics. Oh, one of these is using a 6309 and one is using a 6809, but the software is all written in 6809 right now for the best compatibility. And I'm totally open to relaxing, these restrictions and having a subset of games that use better capabilities. But like I told you, I like to start minimalist. And right now I support CoCoIO and Bonobo cards, and I want to do FujiNet, and maybe some other DriveWire hardware would be suitable. I don't know yet. On that TCP stream, everything flows in little smaller packets that always have a 5-byte header. And the 5-byte header is very reminiscent of the headers that are in the Radio Shack binary formats. Like the first byte in the Radio Shack is either 0 or 255. It's either load me here or jump to this address. And I kind of follow that same pattern, but I define new commands. And N is always the length of the payload that's going to follow the 5-byte header. And in NekotOS, the maximum payload is 64 bytes. If you need more than that, you break it up into smaller pieces. And the idea is, since this is a real-time OS, we don't want to get too slowed down on a large packet. We'd rather do it in smaller bits and pieces so the game flows better. We also give a little better semantics than you usually expect when you see the word packet. Usually you're thinking of UDP packets. Since these are coming down a TCP stream, they're received exactly once, and all the nodes within a a game shard, receive them in the same order too. And you can use that for your game semantics. If there's any question that two different CoCos simultaneously did the same thing, which one actually kills the monster? Well, the rule could be the first one to get it announced in the stream coming down to all the CoCos is the winner. Or the last location you see a monster is the actual location of the monster. But you can depend on that and you can take advantage of it. Let me pause and see if there's questions before I talk a little more about the kernel. And then after I kind of introduce the shape of the kernel, we'll look at actual code for this game. Hey.
Player 0, player 1 want to play Cow Fighter. Do they both have to have the game, or does that come from the MCP?
It comes from the MCP. What they do is they agree on a room number, and somebody joins the room first, and someone joins the room second. The numbers range from 40 to 99. That's your space, because I'm going to use numbers for other things. And so like they say, we want to use room 99. They both join room 99. And then whoever is player 0 within that room is the one that controls the launching of games from that point on. So I scratched my head for months trying to figure out how to do rendezvous, and this works out.
So you're describing that you can self-host the MCP, or you said there's a global...
Can you self-host the MCP, or do you have to use the global one? You can do it either way, yeah.
So what is the limitation constraints of how many active connections can be made?
What's the limitation constraints? How many can... There's no limit how many people can connect to the MCP. That's on a powerful Linux server in the cloud, and it can handle certainly the tiny amount of traffic for a couple hundred people easily. How many can be in a game like this? Right now I have a constant that's set to the number 8. That's arbitrary, but it seemed sufficient. And I did that little calculation at the beginning. If there's 8 players and each one sends 64 bytes once a second, how many interrupts are there in a second? And how many packets do you want to process in an interrupt while you're still doing the game dynamics? That seems like a good starting point. But it's a constant you could change, and if you're doing your own development of a game and you've got your own copy of it to experiment with, do whatever you like. By the way, all entirely open source, MIT license. So very, very flexible. Yes, Brett.
What's a shard?
Okay, in video games, when you have massively multiplayer games, they use the word shard to mean we'll take these dozen players and they'll interact with each other in this shard, and another dozen players will interact with each other in this shard, but all 3,000 people that are playing this game worldwide once don't see all of each other at once. And so right here there's 3 of these marks. One of them is an orphan, which shouldn't be there. I need to do a better job of cleaning up previous connections. But yeah, there's 3 gamers in this shard. But using the same MCP, another 3 players could be in another shard because they created room 89 instead of room 88 to launch the game from.
Is that 1-for-1 with the rooms?
Yes, and that's what the rooms are for. The rooms don't limit your chat like in IRC when you join a room or a channel. It limits who can see your chat. Right now the chat is global. At least while there's not many people. The MCP, yeah. Exactly, yeah. And the rendezvous, when people arrive in the room together, when the game is launched, it's told how many players there are and what your player number is. So you might know that there's 5 players and your player 0, because they'll be numbered 0, 1, 2, 3, 4. And I do want to add it so that the game knows the 3-letter handle of each of the players as well. And I don't have that yet. Boise?
I think 64 bytes for the packet size. How much of that is utilized by the game? Is it shrinking in some cases?
Yeah. This game The packets are probably closer to 12 bytes, and actually they're less, and you can send less, but yeah, it's not has all have to do be 64, yeah.
What is this? What does that end up being? How many megabits per second? Like, for example, is the MCP expected to consume with, for example, those couple hundred players that you mentioned? I'm trying to do the calculation. So it's like 8 times 64 per CoCo playing a game.
Yeah, that sounds like a good starting point. So 2 to the 3rd times 2 to the 5th is going to be 2 to the 8th. So that's only 1/4 of a kilobyte a second per player, which means less than 1 megabyte per second at the server.
Okay, for all those players.
For all those players, that's why I'm thinking it's not going to be a problem. And the server's written in Go, which is has a reputation for being really good at stuff like this.
So, and I heard you say broadcast, but I also heard you say TCP.
Yeah.
So it's broadcast like in the sense that all CoCos are sending a packet on a per second basis to the server, and vice versa, the server sending packet back.
So the packets are all multiplexed into a single TCP stream from CoCo to the server. The server knows who is in your game shard, and there's a certain type of packet that the game can send, which in the code is actually called a game cast. And the server sends that back to all the other CoCos in your same game shard.
Okay, so the broadcast sense is within the shard.
Within the shard, yeah. So if I use the word broadcast, I'm being sloppy. Yeah, it's a game cast
So even in the,
or a shard cast.
So even in the sense, like the gentleman asked a minute ago,
Yeah.
you host your own MCP. You're
Yeah.
not broadcasting on the network.
Right.
In a TCP session.
Yeah. Historically, a year ago when I brought this game, it actually used UDP broadcast.
I thought I heard you say that. Okay.
I did a year ago, yeah.
So, another question, please.
Yes.
I saw there was is there a player hash?
There's not a player hash. There's a 3-letter identifier for every player. The hash that you saw on here was the hash of the NekotOS kernel, because each game is recompiled for every version of the kernel. And if you change, say, the network driver in that kernel, it changes size, and the games load right at the end of the kernel. In fact, the kernel code is divided into the keep forever part and the startup part that you can throw away. And after the startup code runs, the size of the kernel is now this other size, and your games load here. And your game itself has startup code separated from the rest of the code. And when the startup code of your game is gone, then the available memory mark shrinks up for where you've got more memory available.
So that is just a hash of that binary.
Yeah, it's the tail of the MD5 of the .decb lodem format of the game kernel.
Awesome.
Yeah. Brett.
One more question about the chat.
Uh-huh.
When I looked at your stuff online, it looked like you had like you can always go back to the chat.
That's right.
Screen and chat, and then
Yeah.
the game and get back and forth.
Yes, NekotOS owns the break key. That's the only key the game's not allowed to use for the game. And so even while the game is running, you hit break, and the kernel changes what the display is and starts scanning your keyboard. So the game is unfocused, and the chat is focused in. And minimalizing the kernel, here's how the scanning the keyboard and the typing in the chat works. We build the 64-bit matrix, 8-byte matrix of what the keyboard presses look like, where there's a bit for each possible key on the matrix. And we send that matrix up to the server every time it changes. We don't even decode that you pressed space or that you're holding down the shift. We send that matrix up, and that's done by the Go code in the cloud. And what you see on the chat screen, that's not a console driver, really. That's the server sending packets down and saying, poke these bytes into the frame buffer of the screen. The same mechanism as poke these bytes where we're going to play the game binary from next. So we really try to let the server do everything we can that's not involved in really playing a game and free up memory that way. Okay. I could draw this diagram. Imagine a diagram in which the bottom is main, kern, and IRQ. Those are kind of the three bottom modules of the kernel. And main runs first, and that does the setup stuff. And then it launches using the kernel, the very first chat thread. So main is setup and embark. Embark is when it starts the chat process with start task in the kernel. The kernel has start task. It has the network handler, interrupt vectors. The only interrupt the kernel uses is IRQ, and it pretty much owns IRQ. But if you want to do other stuff with NMI or with the fast interrupt, you're free to do that inside your game. You know, anything that's not reserved by the kernel is available to the game. This is a 8-bit platform, you know. There's not a lot of rules. And there's a fatal that anything in the game or the kernel can call to say some assertion failed, that we can't go on from here. The IRQ is used for a monotonically increasing clock. It's kept in three parts. Ticks, which happen 60 times a second. Deciseconds, by definition, there's 10 decis to a second, and seconds. And so if you want to wait for the next 60 hertz tick, you can wait till you see this variable increment. If you want to wait for the next decisecond, you can wait to see this variable increment. And this is how you pace your game so that things happen at smooth rates. You can have events that only happen once a second, like you send your updates to the game state, you game cast them to the other shards. So the monotonically increasing clock is a really useful thing. In addition, there's a wall clock, which I don't know if you noticed when we came in, these were running a clock, and they were an hour apart because this one was in Chicago and this one was in New York. There's no guarantee that your wall clocks are the same, or that they're monotonically increasing, because at like 2 in the morning twice a year, you'll find a discontinuity in the wall clock. Try network receive. So we poll for if packets have come down, and we scan the break key frequently because the break key gets you into focusing on the game and into focusing on the chat. And the chat shell keyboard is always done inside the IRQ. The one thing that moves when you're not playing a game is try network receive moves to foreground instead of interrupt based, so that it can run with higher bandwidth in downloading games and chatting and stuff. There's only two primitives that the kernel uses from the network: send a small packet and try to receive a small packet. Small being 64-byte payload or less. And other things provided by the kernel. There's an allocation pool of 64-byte buffers, and the reason that has to be there is because the kernel needs a place to write packets that are destined to the game. And then when the game says, are there any packets for me, it hands it one of those packets, which consumes it and then has to free it back to the kernel. Those are only used right now for handing packets to the game in an asynchronous fashion. Setting VDG modes. The kernel The game doesn't change the VDG directly. It instead calls an API that says, I want to be in P mode 1, I want to be in P mode 4, I want to be in text mode, because the kernel needs to know what mode it was in so that when you hit escape, or when you hit break, and when you go back to the game with break, it can set that up for you. And there's a little bit of a console that's residual that might go away. And scanning the keyboard for the chat shell is supported. And that's about it. Process states, even though it's multiplayer gaming, it's not multitasking kernel. There's the kernel's own tasks that happen inside the interrupts. Those are special. And there's one main thread that's running. So what state is the kernel in? There's only a chat shell, you're not running a game. There's game visible where you're playing a game. There's game hidden, which is what happens if game was visible and you hit break, where the game continues to run, continues to send the packets, acts just like you're still communicating with it, but you're not. You're communicating with the chat shell. And I want to have a game debug, which would be like a debugging monitor, maybe even a monitor that's aware of your C code and what your labels are in C and looks kind of like GDB or something. Depending on your hardware, if you're using Bonobo, then we could use a software interrupt, and we can use NMI and stuff to do game debugging. And at this point, okay, I talked a little bit about the memory map. Page 0 is divided in half. Half is for the kernel to have direct page variables, and half is for the game to have direct page variables. Direct page variables can make your code shorter and make it faster by using a special instructions that are faster and shorter. A CoCo 1 and a CoCo 2 puts its interrupt relays at address 100. So that's a point that I have to design around. And so I use page 100 through 1FE, essentially up to 200 for the stack. So the stack winds down, and plan on not using more than like 100 bytes for the game stack and 100 bytes for the kernel stack. Don't put buffers inside your auto scope inside your C functions. Put them as globals instead, even if someone told you you should never use globals. This is the 8-bit world, and it's okay. The next 2 pages, the 200s and 300s, are the 64-byte chunks. There's 8 of them that deliver packets to the games. And then at the same place as Radio Shack Basic, your text console comes in. By putting that at 400, it's kind of less surprising. And so if that should have said game hidden. The chat shell, the game hidden, and the debug states can all use that. Kernel variables and kernel itself starts at 600, and then somewhere around 1,000, which is 4K down, is about where the game will start. And it's the same place as the kernel setup code started, which was used once and thrown away. I have not written something like malloc and free yet that can use some available memory between a low mark and a high mark, but this is like available to the game. If you allocate some memory, you move the low mark to say this is no longer available, and you can move the high mark, you can come from each end. Finally, 2 important things, regions and screens. Screens is for the game to allocate the frame buffers it needs. So a P mode 1 or a P mode 4 game need 3K or 6K, and those are at the end of your memory. Like we said, this works on 4K CoCos, and so 4,000 is your RAM limit. The screens, and then regions. I'm sorry? 16K, not 4K. Thank you. Yes, yes. Your screens are at the very end. And then, these games don't use it, but you could declare a region in front of the screen that's common storage across chaining from one game to another. So if you want to split your game into smaller pieces, like an interstitial movie comes in before you go to the next level, and the next level has different code, your game can be split up and chained like that. And if you're in a kiosk mode, then you can write your kiosk as short vignettes that show something and then change the next one. And this is common. But so I want to respect that. If you have to pass some game state to the next phase of the game, you use a feature called regions. When you write a game, all of your code is either called from setup or called from loop. The kernel automatically calls setup once, and then it calls loop repeatedly. If you've done any coding on Arduino, you're familiar with that. And the GNU compiler knows what's called from setup and is capable of putting that in a different section. And that's how we throw away startup code and free up more space after the setup is done. So anything that's only called from setup is going to be thrown away when you get around to calling loop. The stack is limited. The game state needs to get replicated across all the CoCos somehow, so you have to have a strategy for who is authoritative about the game state and how it's communicated and what's to be believed or what's to be questioned, because there could be differences of opinion if you don't design it well. Plan for low bandwidth, target 64 bytes. High latency, like updates once per second. Figure out who's authoritative for each piece of game state. In distributed systems, there's a notion called, I'm losing it now, the ground rules that everybody knows all the time, that's not learned, but is always true. That's called common knowledge. That's the word, common knowledge. So divide the game state, like common knowledge here is that this is 96 by 96. And in fact, in this version of the game, the locations of the cows is fixed. That should really be set up random every time you launch. But right now it's common knowledge. It's hard-coded into the game. But other stuff, like the location of the ships and how fast they're moving, has to be communicated from, or has to be agreed on as people are pressing their arrow keys and moving them around. And so the way this game does it, each CoCo is authoritative for one of those ships, the location of it and its velocity, and once a second sends a game cast to communicate that to all the others, and it receives the ones from the others, and so they get redrawn, and they can continue. Like this is refreshing at 10 frames per second because I use the deciseconds to pace it. Until you get the next authoritative packet, you can continue to draw it where you think it's supposed to be. And then scoring is a feature of the NekotOS that every game shard can assign partial scores, positive or negative, to different players depending on whether they hit them with a bullet or they shot someone with a bullet or what happens. And the kernel takes all of these partial scores and adds them up and delivers special packets that set total scores for you to display. So that's a weird feature of the operating system that it, yeah.
Actually have more than one score for each person that's in the show?
No, it has one. If you wanted to do more, you would have to put it into your game cast packets and in your game logic. But as a service, it does one score. Yeah. And I want it to keep top scores automatically in the server. And as a score?
Yeah.
No, it's a 2-byte number, a 2-byte integer.
Well, 2 bytes is enough.
Yeah, 2 bytes is enough as long as the subfields of the structure add up and don't carry into each other. Because all the server does is sum the partial scores. That's the primitive you've got. You can use it however you like. So who's authoritative for each piece of the game state is the thing you want to figure out in the beginning, how you're going to deal with that. And you can depend on packet arrival order, as I mentioned. And you've now seen the cow glider game, so this is probably redundant. It glides like an air hockey puck that keeps its momentum. The arrows apply forces to it. It's on a 64 by 64 subscreen, and then there's a 32 by 96 over here. That was 96 by 96, where I'm putting the scores. P mode 1. So there's a screen buffer that's 3K. Yep. Now let's actually look at code, so everyone can go to sleep, because here's the C code. This is NekotOS is the repo. Games directory, the cow glider games. What are other games are there? There's the clock that was on when you came into the room. I've got a tiny fourth as a demo. I've got a game of life. There's a space war that's kind of similar to the cow glider. And here's where we first import the kernel API, and then you can choose to import some stuff that I'm collecting in libraries, and you can contribute to libraries if you have some good code to contribute to them. Arc4 is my pseudo-random number generator. Format, I don't know if I'm using format. Yeah, I think I'm not. That does like a sprintf command. Scan the arrow keys in 0 through 7. That only does 2 rows of the keyboard matrix, and that's enough for this game. And some P mode 1 graphics utilities for how to set a color at a specific place. The game runs for 200 seconds currently, and then there's only 4 colors. How are you going to use them? So I divide them into a background color, which is 0. The color my ship is, the color all the other ships are, and then things like the borders and the cows are the foreground color. Now this is a magic declaration to say we want a P mode 1 screen named screen. It's 12 pages, which those are 256 byte pages, so 3K. And this is a magic macro that actually my tool chain looks for these first and allocates those memory. And if we did regions, I mentioned there's regions in which you could pass data in a struct from one instance of a game to another. You would define those the same kind of way you do the screen right there. Anyway, it's not a usual thing to do with C code to put a thing in there that's consumed otherwise. It's more like a pragma, but that's how I decided to do it. Max ships kind of matches the maximum of 8 players, which is what Nekot declares, and the number of players that are playing and your own player number are actually found in this kernel structure. Things that start with a little g for game and then a capital letter are exported from the kernel to the games automatically for you. That's part of the tool chain. Gamecast packet is defined by the kernel. I don't know why I redefined the struct there. Here's a ship. It's 4 numbers, the x and y position and the x and y velocity. And every time you hit an arrow, we're going to change the velocity by 16. Now these x and y, as well as the velocities, are actually fixed point numbers. 8 bits in front and 8 bits behind the binary point. And so this lets me do calculations of something that moves pixel by pixel, where it only moves every couple of seconds. But the fractional part of these numbers is what's incrementing when the pixel doesn't move yet. And the ship state is however many ships there are, we have one of those struct ships for each one of those. And I have one called ship state and one called old ship state. And those go into a region called G0. Since you only get 128 bytes of bulk static storage, the BSS, that's a term from old C compilers. If you make global variables that are big, you should put the word G0'd after them, and then it moves them into a special section of memory that's zeroed and is more plentiful than the 128 bytes of BSS. Now this one goes into BSS, so that's going to be down in page 0 because it's not initialized with a value and it's not declared to be in that other region. So that's some pragmatic issues. My is going to be just a shortcut pointer to my own ship because we use that a whole lot. Num cows, well, it's arbitrary. I made it 32, which is 4 times the maximum number of ships. And what is the state for a cow? Well, the cow doesn't need that fractional part. It doesn't need to be a 16-bit number. It's just an 8-bit X and an 8-bit Y. And I've got a convention that no cow has an X of 0. So if the cow is dead, I set the X to 0. To broadcast the location of a ship, the payload looks like this. There's a type byte that says this is a ship payload as opposed to a kill payload, and it contains a struct ship. And if it's a payload that says I killed a cow, then you have that type and the number of the cow that you killed. There's 32 cows. I don't know if here's the kill. So there's the state of my ship, and there's a cow that I killed. And I don't know that I'm using these others quite yet. Now let's go look at setup and loop. There's loop. Here's setup. So what do we have to do to set up? Well, we have this magic variable my, which is used to point to my ship. And so we know that player is our player number, and so it's the address of our ship there. And then we initialize the screen, which is going to be P mode 1. We initialize the random number generator with some arbitrary text. And it says fix me later because that's fixed. Really, we want it to be some per shard value. Initialize all the cows. Initialize the X and the Y locations of all of the ships. And then we have a function to draw the old ships variable using XOR. And so by assigning the ship state that we just built to old ship state and drawing that puts it on the screen for the first time. We also draw the scores for the first time. And we remember when we started the game because we want to end in 200 seconds. So we use the monotonically increasing clock to get the current number of seconds. That is a 2-byte number, so it goes up to 65536 before it recycles to 0. The last decis that we were used is going to be used by the loop. Okay, so every time we go into the game loop, we check for incoming packets and process them. We look to see if we have advanced to the next decisecond because this paces the game action at 10 hertz. And if we did advance, then that old state is different from the current value, and we remember the new current value. And since decis counts up from 0 to 9, something we want to do once a second can happen when decis is 0, like gamecast our ship locations to everybody and look to see if the game duration is over. I mean, what's going to happen is the time left is going to roll up to 65,000 something from after being 0. And that's when right now we just freeze as our approach to when does the game end. And we've been drawing the timer down in the bottom corner. That happens only once a second. On the other 9 deciseconds, we scan the keys and handle them. If someone's holding down one of the arrows, we want to provide the force to the ship. And then every time through this, which is 10 times per second, advance the ships by their velocity, undraw the ships. Why we're using XOR is we can undraw the old location of the ships and then redraw the new location of the ships after assigning the new location into the old variable. Because remember, this routine always uses the old variable to draw. Now we want to look for kills. So we want to see if the location of our puck, X and Y, matches or is close to any of the cows, and that's just linear search. You look at each cow and see. And then if the operating system has updated the total score, it sets this variable to true. We set it back to false, and we draw new scores. So that is the game logic, and we can dive down into the details where there's a lot of functions here. You know, initialize the screen, initialize the cows, draw the old ships, check the packets, process the packets. You know, a lot of these are functions that are defined up above. But I'm going to pause and see if we got more questions at this point about the strategy that I've used to divide it into setup and loop and keep the state. And yes?
The 65,000 is an artificial insertion.
That's because a 2-byte unsigned number ranges from 0 to 65,536.
And that's the end of the game.
Yeah, and so T reduces to 0, and then it rolls back to 65,000 something. And yeah, that was my way of saying stop, the game is over. And what should happen is you should call an API, which I haven't written yet in the kernel, called game over. And when the king calls game over, that tells the kernel to tell the MCP we finished, and remember the final score as being our score of the game. What happens right now, I don't have that yet. They just go into that infinite loop and freeze. Can everybody write a game now?
I'll have a Fortnite clone for you by noon tomorrow.
Yeah. So this is on the repo. I think I should give everybody a break at this point. My watch is congratulating me for something. Okay, I've been talking for 1 hour. That's about right. We can stop the formal talk and you can come ask more questions, or we can play with this or whatever you want at this point. Yeah?
I may have missed right at the beginning.
Sure.
Too late. When you talked about the games actually loading from the MCP, how do the games get loaded?
How do games get loaded from the MCP?
No, how do you actually initially add one if you have the global?
Oh, okay.
I've created a game. How do I post it?
Right now, you check it into the GitHub.
Okay.
And then it becomes part of the make and publish script that puts it into the global server. It could happen other ways as well. We could build a web UI that lets you type in C code and shows you the compiler errors and lets you define them. And I really have very, very seriously considering doing that. We could also have other languages besides C and assembly, which we would support now. If someone wants to do me a fourth, or write me a basic, or adapt some existing. You're the basic writer. No, that's William. That was William. Yeah. I know there's always lots of basics going on. What other language would you want to write your games in? Smalltalk? I want to build one of those. COBOL? Sure. Yeah, identification division. The regions are inspired by Fortran common blocks. Okay, I'm going to let you off the hook early then.
Thank you.
Okay, thank you. Oh, and here are Bonobo cards. So if anybody has a CoCo and wants to have a card that I have hand soldered and verified works, come take one. And Mark Overhoser's been trying to get a card to work this weekend. I think I have to admit that there's been a regression or something, and this is not going to work instantly. But within the next month, definitely, maybe in the next week, we'll overcome this problem.
Thank you.
That's about $10 worth of parts, if you're curious. That's a Pi Pico 1 is $4. The little chips are about 20 cents. So not a big deal. Who am I working with on this? Mark Overhoser. He's my biggest supporter. Now I want to work with all of you. The GitHub is out there. I'll be happy to help you write a game or a kiosk or a player or something, or your own ideas.
Oh, so for instance, if you wanted to have that repo and you were loading in, let's say it was a kiosk, can you load, does that have to, it's static, once you've loaded that, you'd have to like re-upload something if you wanted some other dynamic content?
Yeah, we don't really have the ability to get dynamic content from elsewhere quite yet, but I do want to put that in there.
Okay.
But certainly one way to do it is structure each, like let's say it's a gallery that's going to show 10 pictures. Each one could be one game. But it makes more sense to me to have one game with 10 preloadable contents that gets reloaded into a screen or a region or something that'll be shared with the next game to run, which is the gallery program. So we need to work on that. I mean, I can also see Basic 09 being the third language that you can write in. And like I mentioned, the software interrupts and other interrupts are not used by NekotOS. They could be used by the RunB interpreter. And we could provide fake response to OS 9 system calls that are needed by Basic 09. That might be really fun to do. Because Basic 09 is fast. You can declare your variables to be integers instead of reals. And thank you.